When analyzing experimental data, should we trust correlation or least squares residuals? In materials science, this choice can change how we interpret XRD, Raman spectra, or SEM results. In this video, we'll see when correlation wins, when residuals win, and why you need both in data science for materials. In data science, we often compare spectra or fit models to data. Two main approaches are correlation, which measures similarity in shape or pattern, and least squares residuals, which measure absolute differences point by point. Let's see how these two methods behave in real cases. Let's start with a true spectrum that has 3 peaks. We'll test 2 reconstructions. Reconstruction A has the correct shape, but the baseline is shifted upward. Reconstruction B has the wrong shape, but the overall error looks similar. Which one is closer to the truth? If we use mean squared error, reconstruction B may look better. But if we use correlation, reconstruction A wins, because correlation ignores baseline shifts and focuses on pattern similarity. Bar charts show that in this particular case, MSE, mean squared error, favors wrong shape. Correlation favors correct shape. Takeaway: correlation is the right choice when we want to compare patterns, even if baseline or intensity scaling varies. Let's extend this. Suppose we have 3 candidate spectra and 1 reference. Correlation helps us quickly identify which candidate matches the reference best. This is why correlation is widely used in Raman spectra and XRD pattern databases for that particular purpose. But correlation has limits. What if we need physical parameters, like peak position, intensity, or full width at half maximum? In this case, correlation can't help. We need least squares fitting. Example: fit an experimental peak with a Gaussian or Lorentzian function. Show overlay a fitted curve on data. By minimizing residuals, we can estimate the background, integrated intensity, peak position, and FWHM to a certain degree of accuracy. These parameters carry direct physical meaning in materials characterization. So, when should we use correlation, and when should we use residuals? Correlation is best for database searches, comparing patterns under baseline or intensity variations. Residuals are best for curve fitting, extracting quantitative parameters, error analysis. In practice, the best workflow is to use correlation for pattern recognition and least squares fitting for parameter extraction. Correlation and residuals are not competitors. They are complementary tools. Correlation tells us which spectra are similar, while residuals let us extract numbers that describe material properties. Knowing when to use which is the essence of data science and materials research. So, we've seen how the choice of objective function, correlation or mean squared error, changes how our fitting behaves. With a good initial guess, the Levenberg, Marquardt, LM, algorithm can find the perfect curve. But what if our starting parameters are wrong? What if the curve has multiple overlapping peaks? Let's take a look at what happens when the landscape gets messy. LM is like climbing the nearest hill. It's fast, but it doesn't see the rest of the mountain range. In the next video, we'll meet a method that can search the entire landscape and find the true global minimum, even with bad guesses. It's called differential evolution, and it behaves more like nature itself, exploring, mutating, and adapting.